Yeah. So, good afternoon, everyone. Myself, Bhaskar Nikam. I'm today going to discuss on use of geospatial technology in soil erosion and sediment yield modeling. So, we'll begin with understanding how soil is formed. We all know soil gets formed due to the process called weathering. Now, the weathering could be chemical, it could be mechanical. Any kind of weathering will break down the parent material into small aggregates, and then the composition of aggregates will decide what kind of soil we are talking about. So you may have higher organic matter content, less organic matter content, soil rich in one or some kinds of minerals due to those presence of those minerals in the parent material. So we have different soils. So you can categorize them based on their texture. You can categorize them based on their infiltration rate. You can categorize them based on their water holding capacity. That depends on what is your end goal, why you want to study this soil. Now, in our present case, we want to see, first of all, we would like to understand what is this process of soil erosion, and then we'll try and understand how we can model the soil erosion using geospatial technology. When I say geospatial technology, I dominantly emphasize on remote sensing derived products, and to handle those products, softwares that we use, the GIS and other processing software. So combining them together, we can call that as a geospatial technology. Now, as you can see here, as formation of soil is a natural process, erosion of soil is also a natural process. So the rate of soil generally in let's say natural landscape, soil erosion rate and natural soil formation rate, they are almost similar, if not exactly similar. And the natural erosion rate of soil is generally called as background erosion or geological erosion. So now we understand that formation of soil is a natural process and erosion of soil is also a natural process. Then why do we worry so much? We worry about soil erosion because over and above the natural soil erosion rate, which we call geological erosion rate, there is something called accelerated soil erosion. Because the erosion of soil gets accelerated due to anthropogenic activities, and that's what we are worried about. Now, there are different agents of erosion. Dominant of these agents are wind and water. Though today our lecture will be mainly concentrated towards erosion due to water and how do we estimate that erosion. But I have kept few slides to make you understand different kinds of erosion that happen due to wind. Now, the erosion of soil that happens due to wind as a agent can be categorized dominantly in three classes, and those classes are suspension, saltation, and creep. So, as you can see, the lightest particle will remain suspended in the air for longer duration. So we call that kind of erosion as a suspension. The heaviest particles of soil will, due to wind, only roll over the surface, which we call as a roll or a creep. And the particles which are neither too light nor too heavy will jump from its location like a bungee jumping, which we call as saltation. So as you can see, for a particle to get eroded due to saltation, it should be between 0.1 mm to 0.5 mm. 65 to 90% of soil erosion that happens due to wind is in the form of saltation. Now, for a particle to erode in form of creep, its size should be somewhere around greater than 0.5 to 20 mm. So 7 to 25% of wind erosion happens in terms of creep or surface roll. And particles which have size less than diameter less than 0.1 mm, due to force of wind they will remain suspended in the air for long duration. They will travel longer distances, and that's what we call suspension erosion, wind erosion in form of suspension. Only 3 to 10% of soil erosion due to wind happens in this form, and you can understand the sand or dust clouds that we see in most of the let's say Arabian countries, or even in India also sometimes, they are caused due to soil erosion in the form of suspension. Now, so if we want to avoid the erosion of soil due to wind, what we can do? One, we can make those particles stick together, which can be achieved by keeping the soil at wet condition. If the soil is dry, the force of attraction between molecules will be less. If there is a water, force of attraction between soil molecules will be high, so they will stick together. Second important thing that we can do is we can obstruct the wind. If we obstruct the wind, its speed will be decreased, and the energy that it imparts on the particles will also decrease. So either we can generate a mechanical barrier or we can generate a vegetative barrier to reduce the effect of wind on the soil. So we'll not dwell on that. Now coming to the next and important agent of erosion, which is water. Now erosion due to water, as the erosion due to wind happen in 3 different forms, erosion due to water also happens in 5-6 different forms, and we'll see each of those forms. So first, what happens is from where we get water dominantly from rainfall. Now the raindrop let's say cloud to earth surface will attain some kinetic. It will have a terminal velocity, it will have mass, so it will have some kinetic energy. Now the moment it touches to the soil surface or whichever surface is touched down, its velocity will become 0. Then what happens to the kinetic energy that it has? It will transfer that energy to the surface, and if the surface is composed of dry soil having particles, detached or loose particles, though the energy that is transferred from the raindrop particles will increase the energy content of those particles, soil particles, and they will be displaced, detached from their location as a splash, and that is called as a splash erosion. Now splash will cause detachment of particles and its transfer nearby area, not very far, somewhere around 2 feet from its own location, it will be detached and it will be thrown away. Now next, this is an energy balance part. Now we also have received a volume in terms of water. So what will happen with that volume? When the soil is dry, soil will absorb that water by the process which we call infiltration. Now sometimes the rate of rainfall will be less than infiltration rate, so almost all the raindrops will be absorbed by the soil and there will be no surface runoff. But in case the rainfall persists for a long duration or the rainfall is very high, so the remaining water, the difference between infiltration capacity of soil or infiltration rate of soil and the rainfall intensity, the remaining water will start rising on the surface, and it will generate a film of water on the surface. If the surface is plain, it will remain there. But generally, the natural surface, natural terrain will have soap either in one direction or many directions. So that film of water will travel towards the downslope area from the higher elevation to lower elevation, or to be precise, from the higher total head to lower total head, the film of water will move over the surface, and that film, that sheet, will move as a sheet, and the stationary soil particles will offer resistance to the moving water sheet. And because the water sheet will have higher kinetic energy or higher total energy, they will dislodge those soil particles and they will carry those soil particles with itself. The sheet will carry those soil particles with itself, and that erosion is called as sheet erosion. Now, due to volume accumulated in the sheet, or due to the topography of that terrain, that water in the sheet will get concentrated into a reel. So there will be a higher volume of water which will increase its velocity, and there will be a reel or gully erosion. Now while that water is getting converted from a sheet to reel, this transition is called as interreel, and there will be a higher amount of erosion than sheet erosion and lower amount of erosion than the reel erosion in this interreel erosion section. So there will be interreel erosion, there will be a reel or gully erosion. Now those gullies or reels will carry that water and will discharge that water in the stream, and stream will have very high amount of water with a very high speed, which will cause erosion of its bank and its, let's say, bottom. So there will be a stream bank erosion. So these are the different forms of erosion due to water. There are other forms also, like there will be tidal erosion, there will be erosion, let's say, a movement of glaciers and snow. But right now we are going to only talk about erosion due to rainfall, raindrop, and runoff. So as you can see, this is how a splash erosion will look like. Now next will be your sheet erosion, then you will have reel erosion, then you will have gully. Between sheet and reel there will be interreel erosion, as we have discussed. Now that the gullies will discharge their water in the stream, there will be a stream bank erosion, and water in the stream will transport that soil and will take the soil out of your watershed, which is a sediment transport, and the soil the water has taken out of your watershed will be termed as sediment yield. So today we are going to see how can we estimate soil erosion, as well as can we estimate sediment yield. Now, so this is a natural landscape, which is a lush green landscape, which is covered with a very good, healthy, thick vegetative cover. So what this does is, this will reduce the opportunity of the raindrop to interact with the soil. Direct interact with the soil will be reduced. So raindrop will be arrested by the vegetative cover, and its kinetic energy will be absorbed by the vegetative cover, and then the water will trickle down through the leaves towards the soil. So soil will absorb. Its infiltration capacity is fulfilled. Even if there is a sheet of water standing on the surface, while the water is flowing over the surface, first the soil will be tightly held by the roots. Second, the vegetative, the stems and the leaves will also offer resistance to the flowing over the surface. So water will have higher opportunity time to infiltrate, and less runoff will be generated. Even if there is a runoff, the chances of eroding soil will be reduced, and this happens continuously throughout the watershed or throughout the terrain. Now if we lose this kind of vegetative cover, if we have a bare soil, then starts your splash erosion. First of all, due to rainfall, we will have splash erosion. The sheet will also carry water. There will be sheet erosion. There will be reel, interreel, and reel erosion. The reels will join together and they will cause stream bank. So this is how the process will migrate, or the erosion will get severe and severe. And now from this situation, it is very difficult to go back to the original state from where the erosion has started. However, let's say somewhere when there was only sheet or interreel erosion, by combination of vegetative measures and mechanical measures, we can still conserve the watershed, or we can conserve the soil in the watershed. Now, just to keep things in perspective, what is the status of soil erosion globally? So as you can see, globally, around 23 billion tons per year is the material that is delivered by the rivers, global rivers, to the ocean. And out of that 23, the 8 billion tons is contribution of, 10 billion tons is the contribution of Asian rivers. So Asia contributes almost half of the material to the, let's say, to the ocean. When we say material, dominantly we are talking about silt flow. This happens because the accelerated erosion rate globally is 16 to 100 times higher than the natural soil accumulation rate. Now, it is generally said that in a standard agriculture practice, it takes around 2 years for 1 centimeter new to form 1 centimeter new soil. 1 centimeter, and this is in standard agriculture practice. The natural soil accumulation rate is even small, even less than the rate in the agriculture area. However, the present erosion rate is 16 to 100 times higher than the natural soil formation or natural soil accumulation rate. If this scenario continues, we are bound to lose 30% of our precious soil resource by 2015. And when I say 30%, I don't mean that only this 30 geographical area will lose its soil and remaining 70% will not. When I'm saying 30%, I'm saying 30% vertically. So top 30% of soil layer will be lost by the mid of this century if we don't act. We have seen the status of soil erosion globally. So what's the scenario in India? Are we behaving differently? Are we at a severe stage of this, or are we at a let's say comfortable stage of this? So what you can see here is the condition here in India is also not very good. Our rivers carry something around, let's say, 252 million tons of silt every year. Out of that, around 480 million tons of this soil, the eroded material, is getting deposited in the reservoirs, which is causing loss of capacity of our reservoirs by 1 to 2%. Now you can imagine we build reservoirs with a standard life of somewhere around 100 to 150 to 100, somewhere more than 100 years also. But if this rate of sediment deposition starts or continues in the reservoir, we may lose our storage capacity at the end of 50 years. And this is a very severe, very serious scenario. Now, Sanaji have published this report back in 2004 and observed data that what is the status of loss of capacity in different reservoirs in India. And what you can see is many of the reservoirs, like Nizam Sagar, the loss of capacity is around 1% every year. And the number goes as high as 5.6% in the Ichhadi Yamuna basin. So you can see we are losing capacity of our major reservoirs at the rate of 1 to 5%. Well, of course, somewhere the sedimentation rate is quite below the expected level, but in many places it is even higher than the expected level. Now you can't allow a reservoir to get sedimented at the rate of 5% each year. So by the end of 20 years, your entire capacity will be filled with soil only, and there will be no water, no place to store water. So it will have detrimental effect on hydrology, it will have detrimental effect even on ecology, it will have detrimental effect on even economics also, because reservoirs perform many operations. The water is stored for drinking, the water is stored for industry, the water is used for hydropower, the water, even the reservoir acts as a flood attenuation structure. So if the entire capacity of the reservoir is filled with soil, the reservoir will be able to act as a flood attenuation structure, and whatever flood wave comes from the upstream, it has to release in the downstream. Whereas after construction of reservoir, the downstream automatically gets developed with the view that now we are no longer vulnerable to the flood wave because we have a reservoir. Whereas the reservoir, if it is not able to fulfill its purpose, if it releases the water in the downstream, there will be a catastrophic effects downstream. On the other side, other dark side of soil erosion and sediment yield is the sediment-laden water will also cause damage to the hydropower stations. The turbines will get damaged, and to avoid this, the hydropower stations are generally kept closed, so they don't function during rainy season. Now see the irony of point. We are monsoon fed country. We receive maximum amount of rain monsoon, and the duration in which we receive maximum amount of rainfall, so maximum amount of runoff, we are not able to capitalize on that. We are not able to use that water due to heavy sediment load in that water. Now we have talked enough about what are the dark sides of erosion. The question remains, can we estimate soil erosion? Of course we can. It's not that you and me are talking about soil erosion today. Scientists have been talking about soil erosion since the, let's say, inception of the theme called hydrology or watershed. So we know soil erosion very well. The question here is, how can we improve our techniques using remote sensing? And that's what we are going to discuss in this lecture. So what I'm going to show you here is a very known, renowned remote sensing, soil erosion estimation technique, which is called revised universal soil loss equation. In short term, we call it RUSLE, or many people know this as RKLSCP. So these are synonyms. So this is a revised universal equation. The method was developed by United States, I think USDA, Department of Agriculture, with the help of Geological Survey, United Geological Survey Department. So original universal soil loss equation was proposed way back in 1965, then 1978 also. But in 1997, Renard has done some revision in this process, not in the original structure of the process, but in some parameters to increase its applicability. And the equation goes like this: and or seasonal soil erosion or soil loss is equal to multiplication of 6 factors R, K, L, S, C, and P, where of course R represents the effect of rainfall on the soil erosion. K represents effect of soil's own property on soil erosion. L represents L and S, basically represents the combined effect of terrain, the topography, on the rate of soil erosion. The C, which we call cover management factor, represents effect of the vegetative cover, or what kind of cover exists on the surface on the erosion rate. And this last factor, P, represents the effect of conservation practices that are applied in the watershed or applied in the area on the erosion rate. Now we'll see each of these parameters, and we'll also see how we can use remote sensing derived products or GIS or make it even better. Now why we are discussing this RUSLE? First of all, as I told you, this is the widely used, widely accepted method. This is a very simple method, requires very few observations, and with very few, let's say, data collections and knowledge of the watershed and the processes, this method can be implemented. This USSI or RUSLE was originally developed for a plot, for a rectangular plot or a square plot, and that's the advantage of this method, because it is originally for a plot or a unit area. This has a potential of, let's say, application in GIS domain. We can consider that plot as a 1 pixel of a raster, and we can apply this method on that pixel. So this has a natural, let's say, ease assimilated in the GIS platform. So that's why we are talking about RUSLE here. So we'll see the study area. So I'm going to show you 2 study areas, one as large as country and another a watershed. So this is a watershed. This is called Nala watershed, Amanga reservoir, and India. So these are the 2 study areas. So what data we require? Let me go back and let us discuss this. So we are saying that we require some factor that represents the effect of rainfall, some factor that represents the effect of oil, 2 factors that represent the effect of terrain, topography, one factor that represents effect of cover, and one factor that represents effect of, let's say, conservation practice. So the factor that represents effect of rainfall, of course, can only be calculated if I have rainfall information. The factor that represents effect of soil can only be calculated if I have soil information. The factors that represent effect of terrain can only be calculated if I have terrain information. Similarly, the land use information and the conservation practice information. So, in turn, I have data regarding rainfall, data regarding soil, data regarding topography or terrain of that watershed or of that area, data regarding what kind of land cover or land use exists in that area, and what are the conservation practices implemented in that area. So let us see how can we derive this information using remote sensing derived products. So first of all, I am talking about digital elevation module. Dr. Arpit has very explicitly discussed what is digital elevation model, what are its application, how can we derive digital elevation model, what are the different sources of the. So here what I have done is, and there are many freely available DEMs of resolution somewhere around 1 kilometer by 1 kilometer to 30 meter by 30 meter. They are freely available. Even a DEM of 2 meter or 5 meter by 5 meter are also commercially available for entire globe. So our point is, if you want to calculate those topography related parameters, you must have DEM. So we have taken DEM, and now from DEM we are going to calculate the topographical parameters. Next is I want to calculate land cover related parameters. So I need land use land cover information. So you remote sensing data, you can generate your own land use land cover. If you don't want to go into all those details, there are freely available land use land cover maps for entire globe. So they are, of course, resolution which is of 1 kilometer by 1 kilometer. So you have spot vegetation land use land cover map. You have NDVS, sorry, Nordic generated land use land cover map. Then there is a Sentinel land use land cover map. Even ISRO IGVP land use land cover map, which is up to 50 meter by 250 meter. So there are various land use land cover maps available in the free and open domain. So either you can own land use land cover. If you don't want to go for that much of, let's say, details, you can take freely available land use land cover map. Now here, we have done some innovation by using NDVI. Now you all know what is NDVI. NDVI is the non-difference vegetation index, which we can safely say is a proxy of vegetation health, vegetation density. So we can say higher the NDVI value, denser and healthier the vegetation. Lower the NDVI value, either the density of vegetation is sparse or the health is not good. So what we have done here is we have taken annual composite of NDVI. Why we have taken annual composite, we'll discuss when it comes to use of NDVI. Then we also have taken soil map. Now in India, the custodian of soil map for national state level, basin level soil map is NBSS LUP, National Bureau of Soil Survey and Land Use Planning, which comes under ICAR, Indian Council of Agriculture Research. So NBSS LUP will disseminate the soil maps. Now, if you don't have that much of, let's say, many of those soil maps are in hard copy, then you need to do communication with them. You don't want to go up to that level. The FAO also has compiled global soil data, and they provide that soil data in open and in. So you can go for that, or you can do your own soil survey. The parameters we are interested in for this model is percentage sand silt clay. If you know that, you can devise what is the structural code of your soil, what is the permeability code of your soil. You have to either you can calculate permeability code, or with the aggregate distribution, you can take a help of standard nomograms and you can decide what's the permeability code of soil. The more important thing that you require in the soil map is the organic matter content. Now, organic matter content is of course property of soil, but it is controlled what kind of cover or what kind of land use exists on that soil. If you have vegetative land use, you are bound to have higher organic matter content in that soil. If the soil is bare for a very long duration, the organic matter content will be minimal in the soil. So organic content is the property which is governed, of course, by the what kind of soil type you are facing, what kind of land cover you are having, what kind of terrain you are having. So this is something which you have to get information from the field, or there are some alternative techniques we'll see in coming slides. Now we are also in need of rainfall data. We can rely on the point scale rainfall data which we get from observatories, IMD observatories. Alternately, we can use gridded rainfall data, what IMD is now providing for entire country, or we can use gridded rainfall data generated from observed data from IMD as well as the satellite observations which is available, or we can rely solely on remote sensing derived precipitation products. I think Dr. Agarwal and Dr. Garg must have discussed about the precipitation retrieval or the precipitation product that are available. We have TRMM precipitation product, we have GPM precipitation product, even ISRO has its own precipitation product. So you can choose whichever data you want to use. Point here is, earlier days when remote sensing was not developed or not that easily accessible, even getting these kinds of data sets was also very difficult. But now whatever I have discussed, all these data sets are freely available. So if one has this, let's say, interest towards working in this domain, data and the processing softwares will now no longer be a limitation. Now, this is an overall methodology that one can follow in calculating soil erosion using Rusley. So, using DEM and doing some operations, the topographical factors can be calculated, which are L and S factors. Using rainfall, the rainfall erosivity factor, the rainfall factor can be calculated. Using soil map, the K factor, the soil erodibility factor can be calculated. Now here I have combined the soil and land use land cover map, because you don't have organic matter content in the soil map that you are having, you can fuse soil and land use map and use some standard tables to generate organic matter content map. So now we'll have soil texture map as well as organic matter content map. You can use them together for calculating of this soil erodibility factor. Now using land use land cover, because if you are working on a larger area, it will be very difficult to pinpoint where what kind of conservation practices are. So what we can do is we can link these conservation practices to the land use land cover and convert the land use land cover map into conservation practice factor map. Something new which we'll talk when the slide of this factor comes. But what I'm telling you is now we are using annual NDVI composite to estimate the cover management factor map. Now let's start seeing what each factor is. So the rainfall erosivity factor is nothing but it is the impact of rainfall kinetic energy on the soil erosion. So of course, higher the kinetic energy, higher should be the R factor. Lower the kinetic energy or lower the amount of rainfall, low should be the R, which is the rainfall erosivity factor. We can say this is the energy per unit time and area, which can be calculated. It is alternately known as EI30 factor, where E is the kinetic energy of rainfall and I30 is the maximum intensity of rainfall during any 30-minute interval. So if you plot an intensity curve of this rainstorm, the higher, if your x-axis, what you can say, if you divide x-axis in 30-minute interval, and if you keep on moving it, the highest value of intensity that you get in 30 minutes is the I30. E is the kinetic energy, I is the average intensity of the storm, P is the total depth of rainfall. Now it is very difficult to calculate this R factor, you require rainfall from recording type rain gauge, because here we are dealing with intensity. If you want intensity of a storm, you require data from recording type rain gauge. Non-recording type rain gauge will only give you depth of rainfall. It will not tell you when the rainfall has happened or what was its intensity. That you can only get if you have rainfall data from the recording type rain gauge. Now, sadly, in developing countries or even in developed countries also, the network of recording type rain gauge is very sparse. Whereas what we have is, we have very dense network of non-recording type rain gauge, because non-recording type rain gauge are there on almost every government establishment, revenue establishments in the district, in the tehsil, even in let's say big villages also. So we get rainfall per day. We don't get intensity of rainfall. To make our life easy, group of scientists from then Central Soil Water Conservation Institute and now Indian Institute of Soil Water Conservation, excuse me, they did this analysis for entire country, and they have developed a regression model between annual or seasonal depth of rainfall and annual or seasonal R factor. So these are the relations. If for annual rainfall, you can use this equation and you can convert annual depth of rainfall into annual R factor. If you are interested in seasonal erosion, you can get the seasonal depth of rainfall and convert it to seasonal R factor. So it was very easy for, now it is very easy for anybody who has knowledge of where to get the data and how to operate that data in GIS environment. What one has to do is, if you are getting daily data, you have to sum it up to convert it to monthly, seasonal or annual, and just multiply the data with some multiplication factor. In case of annual it is 3.8 and add 81.5, and you will get rainfall erosivity factor map for your area. Now that area could be watershed, that area could be basin, that area could be administrative boundary, it could be state, block, region, country, whatever you are interested in. So out of all factors, this R factor can very easily be calculated using this equation given by Rambabu et al. And using rainfall data that is nowadays freely available on many sources. Now, the second factor is cover management factor, which I said we have derived, we have estimated this cover management factor using NDVI composite. Now, to understand this, we have to understand, first of all, please understand that erosion estimated using Rusley, the relation between all the parameters is multiplicative. So erosion is R into K into L into S into C into P. So you understand this is a multiplicative relation. Now for erosion to be zero, what is the minimum condition that we need? The minimum condition that we need is one of these parameters should be zero. No matter what value other parameters have, one of these parameters should have value 0. Now, to make the explanation simple, I'll tell you I have a concrete surface. So there will, of course, rainfall will happen. So there will be R value of R factor, non-zero value of R factor. Then, because the concrete will have some slope, the surface will have some slope. So I'll have L factor, the topographical factors, L and S factor. I will also have maybe, let's say, value of conservation practice factor. But erosion from that area, because it's a concrete surface, erosion from that area will be 0. Now, why will it be 0? It will be 0 because, one, no soil is exposed. So when I am calculating the K factor, if I take into account what kind of surface I am dealing with, I will make K factor is equal to 0. But that I don't know whether this particular block is when I'm dealing with soil map, the soil map doesn't tell me whether this soil is covered with the sediment or that soil is covered with the concrete. In soil map, I don't have that information. So I will invariably calculate the K factor. Just a minute. Hello? Okay. So So the K factor will not be able to tell us whether it is exposed or not. But the conservation practice factor, the cover management factor will tell us, because if the soil is bare, the value of reflectance or value of NDVI will be different. If the soil is covered by water, the value of NDVI will be different. If the soil is covered with vegetation, the value of NDVI will be different. If the soil is bare but moist, the soil value of NDVI will be different. Right? So my point here is, if I know this particular value of NDVI indicates that this particular soil is covered with concrete surface, the value of C factor is equal to 0, and because one of the 6 multiplicative factors, one of the factor is 0, your resultant will be 0. So R multiplied by K multiplied by L multiplied by S multiplied by 0 multiplied by P, the value will be 0. So that's the advantage of multiplication. The parameters will have, a single parameter can have minimal control or can have complete control on the outcome. And this is how the process happens in natural circumstances also. This is how the process happens. The rainfall happens in the urban area, but you will not get any erosion from that area. Why? Don't we have soil there? Yes, of course there is soil beneath your concrete surface. Don't we have slope? We do have slope. We do also have rainfall. There are conservation practices applied there. Then why is there no erosion happening? The cover which is getting exposed to rainfall is reducing the contact between the raindrop and the soil, or completely eliminating that contact, due to which the erosion is becoming 0. So that's the power of this cover management factor. We are using NDVI here. There are 2 reasons for using NDVI. One, NDVI tells me the special difference in the cover. Within an agriculture area, within a forest area, within an urban area, there will be difference in cover. In urban area, there will be some open land or exposed soil available. Within a forest, there will be clearing, due to which the soil will be exposed. Within agriculture, there will be a fallow land or there will be a barren land. So the NDVI image has this ability to characterize these different land covers in a one snapshot. This is a one strength. Second strength, if we take temporal NDVI data, see, in a country like India, vegetative cover will not remain same throughout the year. Vegetative cover will change. Now, during summer season, there will be minimum vegetative cover or almost no vegetative cover. After summer, rainy season starts. So once the rain comes in, the vegetation starts growing. In the middle of rainy season, we will have dense vegetative cover. During winter season also, due to residual moisture, we will have healthy vegetative cover. At the end of winter, there will be a leaf fall. So the vegetative density and the characteristics of vegetative cover will also change with time. Temporal NDVI data gives me this ability to characterize this surface change, temporal change in surface, by using temporal NDVI data. So what, instead of using single date NDVI data, we have used annual composite of NDVI data. Now there are various ways of generating annual composite. You can simply take all 365 NDVI values, and you can average them all. If you know that rainfall, 70% of rainfall happens during monsoon season, 10% rain happens in the winter season, 20% rain happens during the summer season. So what you can do, you can give this weightage. You can give 70% weightage to the rainy season NDVI values. You can give 20% weightage to summer season NDVI values and 10% weightage to winter season NDVI values. And then you can make a composite. So there are various ways of preparing composite. This falls in the domain of digital data preparation and image processing. So we will not dwell on that. But point here is this temporal composite of NDVI better represents my coverage than a static land use land cover map or a static NDVI map. So we have used this composite NDVI map to represent the cover management factor. Now, you all know NDVI value 1 means very dense, healthy vegetation. If that is the case, a very healthy, dense vegetation, we can safely assume that erosion from that area will be minimal. Now, for mathematically, for erosion to be minimum in Russell equation, the value of C factor should be minimum. Mathematically, minimum value of C factor could be. So, hypothetically, what I am assuming is if NDVI is equal to 1, C factor should be 0. You all must be agreeing with me. NDVI 1 means dense, healthy vegetation, which will minimize or maybe completely stop the erosion from happening. If there is no erosion happening from that area, value of A of Russell equation R into K into L into C into P LS CP is equal to A. So the value of A should become 0. Now, when can it become 0? Either one or many parameters are 0. Do we have rainfall there? Yes. Do we have soil there? Yes. Do we have topography there? Yes. So all these parameters will have value, some value, non-negative, non-zero value. So to make that soil erosion 0 or reduce it, I must reduce value of C factor. The minimum value of C factor could be 0. So mathematically, hypothetically, I am saying NDVI is equal to 1 means C factor is equal to 0. Now, if NDVI is equal to 0, what that means? That soil is exposed. It's a dry, exposed soil. If it is a wet soil, the value will be slightly negative, 0 and slightly negative. If soil is dry and exposed, the NDVI value will be somewhere around 0. Soil is exposed means what? Or there is no vegetative cover means the erosion will be highest, or rather the erosion will be controlled by type of soil, kind of rainfall, kind of terrain, and not by cover, right? So you remember I said that individual parameter will have either no control on the outcome or will have complete control on the outcome. So in first case, when we had a thick vegetative cover, the C factor gets the complete control on the one, so we put its value to be 0. When there is a no vegetative cover, the C factor, the cover has no role to play in the erosion process, so we put value is equal to 1. In multiplicative equation, if a parameter gets value 1, which mathematically means this particular parameter has no control over the process. This is a free parameter. This cannot control the process. At this state, cannot control the process. So what I'm trying to indicate here is when NDVI is equal to 1, C factor will be 0. When NDVI is equal to 0, C factor will be equal to 1. This gives me idea that would be an inverse linear relation between NDVI and C factor. And if I just show, I can join 2 points with a straight line. So I'll join that line and I'll calculate the equation of that line, y is equal to mx plus minus c. Set, and in this case, what will be the highest value of NDVI? 1. Lowest value for our case 0. What will be the highest value of C factor? 1. 1. Lowest value 0. So if I plot that reverse curve, I can generate that equation, which will generally have, let's say, slope and a offset. Okay. So this equation helps me to convert NDVI into a C factor map, and this C factor map will have a better representation of cover than any other concept previously. Now moving towards third factor, which is a soil erodibility factor. What you can see traditionally, it is calculated using this product of primary practical size fraction, then organic matter content information, code information, and permeability code information. So this M is nothing but percentage silt plus percentage very fine sand multiplied by 100 minus percentage clay. So lesser the amount of clay, higher value of M. Higher the amount of clay, less will be the value of M. Now, why this impacts? Because the M is in the numerator of K factor, and K is multiplicative factor in Russell's equation. Higher the value of M, higher will be the K factor, higher will be the erosion. Lesser the value of clay, higher will be the M, higher will be the K, higher will be the erosion. So, which tells us that if small clay particles in your soil, if they are less, you are susceptible for higher rate of erosion. If the clay particles increase, the susceptibility of soil will reduce. So now, using soil map, either you can use NBS LUP map, you can use your own map, you can use FAO map, you can convert that map into a K factor map. Now I told you conservation practice or conservation support practice factor. It is generally this information is generally taken from field, but for a larger area it is very difficult to get this information from the field. So what we do is we link these values to what kind of land use land cover we have. For example, agriculture in India, every agriculture field will be demarcated by the bund. Now those bunds serve multiple purposes. Those bunds, the boundary bunds, they help individual farmer to recognize its own jurisdiction. It also helps to conserve water, the water that the farmer is giving through irrigation, or the water the farmer is receiving through rainfall. It also helps the farmer to conserve soil. So those bunds actually act as a conservation practice. They reduce erosion from that particular agriculture plot. Similarly, in urban area also, the drains that we have constructed, the buildings that we have constructed will offer some resistance to the flowing water and will reduce the erosion and sediment yield. So what we do is, from a standard literature, we take out these values, we link these values to what kind of land use land cover we have, and we convert the land use land cover map into conservation practice factor map. Now coming to very important factors in estimation of soil erosion, the terrain factors, which are slope length factor, L factor, and slope factor, which is the S factor. Now we must understand this concept, slope length factor. The effective topography of erosion in loose clay is accounted by the topographical LS factors. The erosion increases as the slope length increases and is considered a factor. This is the L factor. Now, what is slope length? It's a very important definition which you must understand. Slope length is defined as a horizontal distance from the origin of overland flow. Now, from where overland flow begins? Overland flow generally begins from the ridge, watershed divide. Okay. The horizontal distance between the point from where overland flow begins to the point where either of these conditions are true. What are the two conditions? Where the slope gradient decreases enough that deposition begins. So horizontal distance between the ridge point and the point where slope is so gentle that so between these 2 points is called slope length, or the point where runoff becomes concentrated into a definite channel. So from ridge to the start of channel, the length, horizontal distance is slope length. Now, before remote sensing or technology, people used to face huge difficulties in calculating the slope length, because how to identify the second termination point? We always know where the watershed divide is. That's how we delineate watershed. But how to find out either of these 2 points, these 2 points, where the gradient decreases or the runoff gets concentrated? We'll see in 2 or 3 slides. So the equation for slope length factor is slope length divided by 22.13 raised to this variable slope length exponent. Now you might wonder, what is this 22.13? 22.13 is a standard plot size of using the plots, the data of which was used to develop this equation, this USLE or ROOST. The original plots on which they have done multiple experiments were of 22.13 length, slope length. So the slope length of this plot divided by 22.13 raised to variable slope length exponent will give me slope length factor. Now how to calculate the slope length? Of course, this variable slope length exponent can be calculated using slope map. We'll see in coming slide. But to calculate slope length, a very important input that we get from remote sensing is DEM. You all know what is a DEM. You must be aware about digital surface model and digital terrain model. In most of the hydrological modeling activities, we prefer digital model, or other way also we call it as a bare earth model. So this is how it looks like. This is how surface model. This is the surface model looks like. This is how the digital terrain model looks like. You all know if we remove the man-made feature, the vegetative cover from the surface model, we will get digital terrain model. Now using DEM, we can calculate slope. You all must have seen D8 algorithm, how we calculate slope. So this is a D8 algorithm. We can also calculate direction of slope. So not only the value of slope, we can calculate direction of slope. We can tell which pixel contributes to which pixel. And that helps us in calculating flow accumulation. So because we know direction of flow of each pixel, we can calculate flow accumulation. Basically, this flow accumulation value tells me how many upstream pixels are contributing in this particular pixel. So with this knowledge, you can understand the pixel flow accumulation value 0 are the rich pixels. So you can understand the initiation of L factor, slope length, happens at the ridge. So initiation of flow happens here. So these all are the ridge pixels, and this is the point from where the surface flow begins. Now the flow accumulation tells me how much length the flow has traveled. And stream generation threshold tells me after how much accumulation stream gets generated. So all the pixels having flow accumulation value less than stream generation threshold tells me the distance the flow has traveled on the surface to reach up to this point. So we can exploit this to calculate the slope length factor using DEM. Now, there are various sources of DEM, which I think Dr. must, so I'll not dwell on this because we are already short of time. There are various sources of DEM nowadays, very good quality accuracy check DEMs are available. For India, we also provide DEM on Bhuvan. The Cartosat DEM is available. Cartosat DEM of higher special resolution, 10 meter special resolution is also available, but that is a paid product. There are other paid products also, like Digital Globe provides you DSM of 50 centimeter special resolution, but this is a commercial product. So there are various sources of DEM. Now coming back to our decision, this variable slope length exponent can be calculated. If you know slope of the terrain, slope you can calculate using DEM. So once you have slopes, you can calculate this variable slope length exponent M. And this particular slope length factor can be calculated. Slope length is the horizontal distance from where the overland flow begins and the point where it gets concentrated into a stream. So basically, flow accumulation of all the pixels having flow accumulation value less than stream generation threshold multiplied by the grid size will represent this slope length. So flow accumulation into grid size divided by 22.13 raised to m will give me the slope length factor, provided this flow accumulation value of the pixel is less than the stream generation. So now once you have calculated that, you have calculated the S factor. Now you want to calculate the slope steepness factor. L is the slope length factor, S is the slope steepness factor. As I told you, Roosle was modified because originally USNE was designed for agriculture watersheds. But because of its simplicity, its robustness, people started using it for all the watersheds, hilly watersheds, forested watersheds. Because when I say agriculture, dominantly agriculture is practiced on the slope less than 9%. However, other watersheds will have slope way beyond 9%. So those equations developed for slopes less than 9% may not be applicable for other slopes. So McCool in 1993 has put forward two equations, one set of equation for pixels having slope less than 9% and other set of equation for the areas having slope more than 9%. We can calculate slope using DEM, and we can put a conditional statement that if slope is less than 9%, use first equation, and if the slope is greater than 9%, you can use second equation, and you can calculate the S factor. And then you can multiply RKLSCP to get soil erosion map. As we have got in front, as you can see, the map which is available in front of you. Now we have done validation of this exercise for basin scale, and what we could see is, let's say, the average erosion rate that we have calculated for entire country is somewhere around 18.69 tons per year per hectare, whereas the Central Soil Water Conservation Institute has published that to be 16.5. So comparable. For Ganga River, the erosion rate that we have calculated is of the order 11.56, so 6 tons per year per hectare. There were two publications that we came across. One publication says that erosion rate in Ganga basin is 5 to 10 tons per year per hectare, and another publication says it is 10 to 20 tons per year per hectare. So we are in the middle of both of these. So we thought that, okay, whatever we have calculated is a good result. And you have to understand, both of these publications, 1992, 1987, remote sensing and GIS, somebody has texted me something, remote sensing and GIS was in very primitive stage. So we were bound to have result, whereas nowadays when we have done it, remote sensing data are widely, the products of remote sensing, the data that we get, they are quality checked. So the error that creeps in your calculation due to errors in data or observations will be minimal with the increase in time. Now this is how soil erosion. But the problem is, we cannot validate soil erosion because we don't measure soil erosion. We measure sediment yield. So how do we measure sediment yield? We put an observation station at the outlet of station. Sir, is there any R package available? We'll take questions maybe after some time. Finish. I have a few more slides. I'll finish them and then we'll talk about the Q&A. So we cannot validate soil erosion. We observe sediment yield, which is a, let's say, which is a yield of the amount of soil the water flowing out of my watershed carries, which I measure at a particular point. So it's a point scale observation. It's not a distributed observation. Whereas soil erosion is a specially distributed phenomena. So I can't validate soil erosion if I'm observing only sediment yield. So what I need to make my model calculate sediment yield. And that's what I've done. That's what the models are available using same technique, using same let's say equations or the parameters which we have used for soil erosion. Where what we have done here is we have done that calculation in 2D domain. So R factor is same, K factor is same, C factor is same, P factor is same. Only the terrain factors, earlier we have calculated them in 1D domain. Now this LS2D will be, the porphyral factors will be calculated into 2D domain. Now how do we do that? This is how we calculate this LS factor. This LS is equal to this specific area of a multiplied by 22.13, then sine of slope raised to n, which is also constant. What is the specific area? The specific area is upslope area divided by the perpendicular to the flow length. So you can say overland grade per unit width normal to flow direction. Basically, if your flow is coming from the side, the resolution of your pixel, it becomes WN. If it is coming from the corner, then this is of this square becomes the WN. So we assume here that the flow enters in the pixel from the sides. You don't want to assume it, you can take help of flow direction map and you can find out from where the flow is coming here, whether it is coming from the side 4 pixels or the corner 4, any of these pixels, and you can calculate this LS factor. Once the LS factor is calculated, you can multiply that and calculate the soil erosion. We can use same parameters as RAAS to calculate transport capacity. But to calculate transport capacity, we also have to one transport capacity coefficient, which will in turn be used to calibrate the model. So again, this K is R is same, R is same, K is same, A and S is also same. This KTC is the general value of KTC 1 into 10 to 5 to 2 into 10 to 4, depending upon what kind of land use land cover you are having, what kind of soil you are having. And then what we'll do, we'll calculate the transport capacity. We have gross soil erosion. We will take help of DEM derivatives. So we'll take flow direction, accumulation, and slope map. From this, of course, we'll calculate the LS factor, AS factor. We'll calculate the gross soil erosion, which is A of loose lay. We'll again calculate the transport capacity, and then we will route the sediment. We'll compare the loose soil, the erosion of each pixel with the transport capacity of each pixel. If erosion is less than transport capacity, the entire eroded soil will be transported to the downstream pixel. If erosion is greater than transport capacity, then only the amount equivalent transport will be transported to the downstream pixel. And then we will use the output, the sediment transport output at the outlet, and we'll compare it with the observed data. If it matches well, all our assumptions appears to be true. If it doesn't matches well, then we'll go back, we'll change the value of KTC, which is a transport capacity coefficient. We'll again calculate transport capacity. We'll do this exercise again until and unless we get the correct value of sediment transport. Now, how do we do this sediment transport? For that, we take help of flow direction, gross soil erosion map, and transport capacity map, and flow accumulation map. Now, why flow accumulation map? Because flow accumulation map tells me whether this pixel gets contribution from other pixels or not. So for pixels that contribute to other, we only compare the gross, so the rich pixels, only compare the gross soil erosion with the transport capacity. If gross soil erosion is less, it will be carried. If gross soil erosion is more than transport capacity, the transport capacity amount of soil will be carried, and remaining will be deposited in that pixel. Now that pixel, this particular pixel, with the help of find out where it contributes. So this pixel contributes to this pixel. So the sediment transport of this pixel will be added in the gross soil erosion of this pixel. So now it will have its own soil plus soil coming from the upstream. Then we'll compare this available soil with the transport of this pixel. Again, same thing, whichever is minimum will be carried and remaining will be deposited. We'll find out where this pixel contributes, and then its sediment yield will be given to the next pixel, and the process will go on. Now to do that, we code using both Ideal and Python, and this code goes on calculating the sediment yield up to the last point. We have also developed a user interface which we have named as sed yield, so which helps you to calculate which does the hydro processing, which calculates the erosion, gross soil erosion, which calculates the sediment transport capacity and sediment yield, and then it can be used to validate. So we have to give the range of KTC, and it can validate using model efficiency and relative root mean square error. So you can see this is how the gross soil erosion will look like. This is the transport capacity of that area. As you can see, the transport capacity will be controlled by the flow accumulation. This is a sediment yield in that area, and this is a sediment erosion. And surprisingly, higher deposition was observed along the stream. I'm not saying in the stream, I'm saying along the stream, which is naturally true, because along the stream the slope becomes gentle. And because the slope is gentle, the transport capacity of those pixels suddenly reduces, whereas the water coming in those pixels will have higher sediment flow. So higher amount of deposition happens along around the stream, the pixels near the stream, which is naturally also true, and the model also represents it. Now you can see after doing many iterations of KTC value, the model has found the optimum value when model efficiency was highest and relative root mean square error was lowest. So that value is selected as optimum value of KTC, and then the validation of the model is done. What you can see here is the results were fairly accurate, where model efficiency of 0.62 and relative mean square error of 0.12. And this is how this is the value of relative error, and this is how we can calculate sediment yield from the watershed. I also have many slides, but because the time is not available, we will now switch to Q&A, and I'll take up the questions. Let me see from where I can get these questions.